The big break in the art of reinforcing the concrete came with the introduction of pre-stressing. The idea of pre-stressing, conceived and put to practice in the 20th century, is the single biggest happening of the greatest significance in the entire history of construction on this planet. The man who first gave the form and content of this concept, the originator of pre-stressed concrete idea, was none other than the greatest of greats, the master designer, builder, genius of all time, Monsieur Eugène Freycinet, a Frenchman, the greatest civil engineering visionary of all time. Here is the man. A lesser man would have been contented with the fame and fortune he had in 1930s, because he was an inventor par excellence. He had money from all the patents in the world. But Freycinet was a man with a mission in his heart. His life carries an obvious message. His bitter struggles for 7 long years for the cause of pre-stressed concrete made history. If history has to have its heroes, here was one for the history of bridges. Freycinet took patents in 1928. He was out to sell the history's most exciting building material called pre-stressed concrete, but alas, with no buyers around. The same problem of mindset. He had reportedly told his friend, Saint Le Corbusier, he told him, he says, and translation again, both are French, he says, I reached my goal, now I am looking around to see what I can use this discovery for, and who will accept it. How do I convince them? These are his desperate words. And he continues, he says, and in my opinion, the modern society needs it for all their housing and their highways. Way back then, 1930s. Corbusier was so touched by the sentiments of his friend as to conclude, and he said, into that one short sentence that Freycinet wrote to him, he says, he has crammed a vast wealth of poetry, lyricism, solidarity and concern for mankind and for the hearts of human beings. In 1960, the beam bridge, can we stop this fellow? It's a little, which switch is this? I don't want to touch them all. In 1960, a beam bridge, I don't know which one, I'm sorry, I would have done it, but I don't want to, don't switch off the computer. Oh, good, you won. Thank you. In 1960, the beam bridges had already reached spans of up to 160 meters. And master engineer Ricardo Morandi, I was telling you about, the great, you could just sit in his company and by radiation he would transmit his knowledge to you. He was one of the greatest, but very, very mean man. He told me, he used to tell that to everybody else, if we wanted more salary, which we did need, no, if you work with me for 2 years, that will last you a lifetime. You just need to survive, that's it. And that was 100% true. And you look at this mastermind then, the first person who did the cable-stayed bridge way back then, and across the Lake Maracaibo in Venezuela. Bridge across Lake Maracaibo, here it is, in Venezuela, and was under construction with spans of 235 meters each, about 800 feet, already using cable stays then. Here is the great man, Professor Ricard. These professors are professors who are practitioners more than teachers. They understand the ins and outs of what they are doing. This is his famous bridge across Lake Maracaibo in Venezuela. This is his famous, one unit, one element, Maracaibo view of the main span. You could see how the stresses would flow. The live load would be picked up by go to the beams, picked up by the stairs onto the pylon, down into the foundation. Everything is simply supported. Not simply supported, but statically determined. This is his famous Morandi table. Same bridge, but very difficult for maintenance people. They have to look for cracks and distresses at 1 million angles and cross sections. But that was not, he did all the bridges across, in west of Italy along the coast. That's called the Sun Highway. That's called the Autostrada del Sole, the Sun Highway. There are first-class bridges in that. Each bridge is different than the other, and each bridge is more complicated than the other. because it is coming from Morandi, nobody could question him. But these are, you can see them for a lifetime. You should go abroad. This morning we had 2 hour, 1.5 hour session. I don't know how many of you came, but that's where I was explaining quite a few things. Then, remember this, it's not the analysis that you start. You give me a problem, you straight away open your laptop and start. Don't do that. That's not the way practice is done. You have to conceive the idea. You have to draw sketches to scale. Then you have to transfer those sketches to the drawing board, make them and chisel them and chop them and cut them short here and there till it looks something and you can see the stresses flow. Then you start the analysis. Then comes the design. And in so doing, you have to fix the cross-sectional dimensions first. That doesn't come by you starting your laptop. Now this, why I'm saying this, now this one, I will first show you the next one. This is a bridge across, this is the Paraná bridge across Chaco Corrientes in Argentina. You just look at this bridge. But the designer who had to conceive it, this is how the conception started. You have to actually physically see the big books, big notebooks that they have. I have seen one in Madrid. There's a big bookshop. That's where Leonardo da Vinci's sketches, the big book containing the sketches, that book is about 1.5 meters by 2 meters. Nobody can lift it. And these are original sketches. You see them, you will drop dead. That is engineering, not starting with this calculator. You will then begin to realize how the conception of structure and understanding commences. So this is what, I can't use your damn thing, this thing. This is how the conception started, and this is what he did. Just to transfer the idea that please, computer pile of your printout is useless and meaningless. You have to understand differently. 70s, the longest span of beams reached 230 meters in Japan. And for cable-stayed concrete bridges, designs had been made with about 300 meter spans then. Today we go up to 500 meters and even longer. But this is then, 1970. The achievements in building long-span bridges in pre-stressed concrete are too close to our times. You know, that is like yesterday, not good old steel bridges of wrought iron and cast iron. So it is not easy to comment on the bridges that have come up in our own, in the same decades as we are living. So that's why I'm saying that the achievements in building long-span bridges in pre-stressed concrete are too close to our times to afford a historical perspective or comment. But the development of new landmarks in span, in form and construction technology is growing at a dizzy pace. Now you see, this is again Professor Christian Menn of Switzerland. This is the Ganter Bridge, Simplon Pass in Switzerland. If you look, now this is a picture taken against the sun. If you see the same bridge along the sun, this is how it looks. And imagine if you see these two fellows, this way or that way, when it is snow all around, you freeze. You just cannot do anything other than appreciate. And he's one of the greatest analysts of the day, Professor Christian. I don't know whether he's dead soon enough. I don't know when, but if at all. Then this is one of the latest, Millau. I used to call it Millau till I was corrected. It's pronounced, I'm told, as Millau Viaduct. This is between Barcelona, between Spain and France, but between Barcelona and Paris. Now this, see this very carefully. This is not a joke. This bridge is something superb, absolutely superb. This is across the motorway A75. Each span is over 1,000 feet, 2.5 kilometers long, and the pier height is taller than the Eiffel Tower. And I'll show you that. Now you begin to see what this bridge is. Now I'll show you a picture or two of this bridge during construction above the cloud line. Bridges is a great topic. Please take to it. This is once it was completed in daytime, And this is when it was taken at night time. The originator of construction in the free cantilever method, because if you have to cross bodies of water where you cannot raise the staging from bottom up, you have to do something else from top itself. So that's called the free cantilever construction method. The propounder is Professor Dr. Ulrich Finsterwalder. Yes, Professor Ulrich Finsterwalder, one of the greatest bridge builders of our times. Now, here's the great man. A later modification. Now he would do segments on both sides, pre-stress them together, again segments on both sides, pre-stress them together, and keep going outwards from the pier, do the same from the next pier till the two cantilevers would meet. But these were all cast in situ, cast in place segments. Somebody else came later, he did the same thing, but he converted the technology into using precast segments. And that was Jean Mueler, J-E-A and Jean Mueler, a disciple of Freycinet and Guillaume's school of thought. A later modification of this method in the cantilever construction with precast segments was introduced in '63 for the Choisy-le-Roi Bridge in Paris and Oleron Bridge on the French coast, I will show you, by a contractor, which was a contracting company. The consultant was STUP, S-T-U-P. It's an acronym. S stands for something, T for something, U for something. STUP Paris, which was owned by Freycinet. Freycinet was a great legend. He would give the problem and he would give you the solution. He wouldn't tell you how. And he wouldn't perhaps even know. But a great mathematician turned engineer turned mathematician named Yves Guillaume. He used to be with him all the 24 hours almost. He gave mathematical proof of everything that Freycinet propounded. And he married his daughter as well, because he was there for too long. Now, but the idea is not marrying the daughter, which you can. But the idea is, these are the mating of the great minds. Please, this is not a lecture meant for just a lecture. You take it seriously. This is blood-curdling experience. This was Jean Mueler. I have said it somewhere, most famous Freycinet-Guillaume method. This one, I think it must follow. No, I must have said it somewhere. 63, and the name of the company was Campenan Bernard. Campenan Bernard, that's the French. Operating under the most famous Freycinet-Guillaume school of thought for bridge culture and thought. This was done by Jean Mueler, who is dead now, very recent, 3-4 years ago he died. This is his bridge. When he lectured on this in England in 1963-64, I attended his lecture. Now when you listen to people like these, you are transfixed, because they give you certain ideas which come into the caudal domain maybe 2 decades later. Like for instance, what is the creep loss difference between a cast in situ segmental construction and precast segmental construction, and the thickness of the joints, whether you should do mortar joints or whether you should do epoxy joints. Epoxy came later after this. This was mortar joints. And the deflection, you calculate in cantilever construction, as you build the cantilevers, they keep deflecting. Now you can't have a bridge like this. So you have to in advance pre-calculate the possible effect of creep in deflection and introduce those deflections in reverse. Okay, good night. Introduce those deflections in reverse. That's called the camber calculation. That even today computers have to be used in order to predict with the correct creep coefficient. What they did in '64 when there were no such knowings, that's when you listen to them you get to know. Then this is the Fel-senau Bridge in Bern. This is the great Holland Bridge in Sweden, cantilever construction. Our own. No, this is the Eastern Schelde in Holland. This looks very massive, but mind you, each span is 300 footer. It looks massive because everything is so fat and big. Everything is precast. The piles are precast, the pile cap is precast, the inverted V-piers are precast, the deck is precast. And you can see the effect of the double attack of chlorides and sulfates. You can see that through the stain marks. Each span is about 300 footer, 5 kilometers long. This is our own Gauranga Setu. There are many. There are hundreds in India now. This is the Patna Bridge, which is now in very bad shape. It's not, I don't want to say anything because I was also associated with it through governments. This is my first really long bridge, 26 kilometer long, Bahrain, Qatar, sea link. 26 kilometers, which had about 14 kilometers of bridge, no, 18 kilometers of bridges, and the rest was a number of man-made islands. Why islands? Because one, you needed the place for space for passport offices, administrative offices, etc., etc. Second, the depth of water was so low that it wouldn't be right to do a bridge, you had to do filling and embankment. Then there is the Orado Bridge.